Hey there, this is Horner, and this is the File Exam Review Key. The reason I'm going through it is because I think there's little things that you have to notice as you take a look at it. So they want you to draw a quantitative motion map. So remember, the word quantitative means that it needs to have numbers. You have a bicyclist going at 10 meters per second for 6 seconds. So here's 10 meters. Notice that we went 1 second to go that 10 meters. We go another second, goes to the next 10 meters, and then it just kind of makes its way on from there. So that's probably the easiest way to kind of see what's going on. Let's count the time. So 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Notice that the arrows tell me how many seconds have elapsed. The dots just tell me where it is at a particular time. So at 0 seconds, it's at the origin. At 1 second, it is at the 10 meter spot. When it gets to the 6th second, at that point, it stops for 1, 2, 3 seconds, and then it's going to travel 1, 2, 3 more times. And notice this time it's only 5 meters per second. So the length between the dots here is shorter than it is for the others. Notice that these are a full 10 and these are only 5 as they go through. So that's what you want to see. On the next one, it wants us to draw and label a quantitative position versus time graph for the motion map below. I would start at the first dot, put a 0, and then put your numbers all the way through. So now you see kind of what it's doing. Our position versus time here, it starts at 1 meter. So we'll let's go ahead and make this a little bit smaller so we can kind of see what's going on. We've got it starting at 1 meter. So there's the 1 meter. Here is our 0 time. Position in meters, position versus time. And you'll notice down on the bottom, we've got time in seconds. At 0 seconds, we've got 1 meter. We've got at 1 second, it's at the 2 meter spot, 2 seconds, 3 meters, and it keeps going until it gets over to 4 seconds, and that's where we hit the 5, and then we just stay there. So that is your graph, and that's what that graph should look like. They want us to use a graph now to answer some questions. Your graph has been fixed so that the numbers should line up really well. They want us to describe the motion, so we just say it starts at 15 meters, so always where it starts. What it travels, so we're going to say that it travels at a constant velocity, and it does that for our 1, 2, 3 seconds. So it does it for about 3 seconds. Actually, it does it for about 3.5 seconds. When you look at the graph, you'll notice that it travels for 3.5 seconds. So to find the average velocity, remember average velocity is the change in position over the change in time. So we're going to go 50, here we've got 50 minus 15 divided by 3.5 minus 0. And if you do that math, you should get 10 meters per second. The mathematical expression is really just the physics equation. And our physics equation here is position, that's what's on our y-axis, is equal to our slope, which is 10 meters per second, times what is on our x-axis, which is time, plus whatever our y-intercept is. And here it's 15. So notice it crosses the y-axis at 15. Assuming that the motion remains constant, they want us to determine the position at 10 seconds. So we're going to use the same equation here in equation form. And we'll see that we just end up with 10, which is our original velocity, times our time, which is 10 seconds, plus 15, and you should get 115 meters. For the second page, this one says, shown below is a velocity versus time graph for an object. They want us to describe the motion, so we know that it moves in the positive direction because it has a positive velocity at 4 meters per second, and it does that for 2 seconds. It moves in the negative direction at 3 meters per second for just 1 second, and then it is at rest for 2 more seconds, so it stops for 2 seconds. They want us to draw the corresponding position versus time graph and number the axes. So here we go. We're going to start at 0. We know it travels 4 meters per second for a second, travels another 4 meters per second for a second. After that, we see, if we go back, that it travels at -3 meters per second for a second. So I've got to go down 1, 2, 3, and over 1. And now I've got it where it is at rest for the next 2 seconds. And so that's kind of what they told us to do. And I'll blow this back up to 100%, and hopefully it won't turn blue anymore here. Doink, doink. Alrighty, here we go. How far did the object travel in the time interval 1 second to 2 seconds? So I can do this very easily just by going from the 8 down to the 4. And so we know that during 1 to 2 seconds it traveled 4 meters. They want us now to find the displacement from 0 to 5 seconds. Remember, displacement is different than distance. Distance would be the entire thing, and we just want displacement, so that's from the 0 to the 5, and that's just the dotted line here. So I'm going to take my final position, which is 5, minus my original position, and that's my change in position. So I subtracted my initial position from the final position to get that 5 meters. To find the average velocity from 0 to 5 seconds, we've got to take our change in position, which was 5, divided by 5, and that's 1 meter per second. So all we had to do was find the slope of the line connecting that 0 to 5 seconds. So from 0 to 5 seconds, we found the slope of the line. After we find the original velocity, they want us now to, the average velocity, they want us to find the average speed. Remember, speed is equal to the path length divided by time. So we have to add all of the distances and divide by 5 seconds. So if we go back, we see that the first distance is, or the first path length is 8, and then we go 3, and then we don't go any. And so we're going to add 8 plus 3, that's 11, divided by the 5 seconds, and so our average speed is 2.2. Remember, our average velocity was only 1 meter per second, so big difference between the two there. A bird travels towards 0 position and suddenly reverses direction. They want us to find the average velocity again. So remember, average velocity is going to be the slope of the position versus time graph. And they want us to do it from 0 to 10 seconds. So from here to here, we just need the slope of this line. Notice that it is negative, and it is -2. The average velocity from 10 to 20 is going to be 25 minus 10 over 25 minus 10. And it's because I've got, if I get here to 20, I could just see that this line, I need to find the slope. So I've got 25 meters minus 10 meters over 25 seconds minus 10 seconds, and that gives me 1 meter per second. The very last thing they want us to do is find the average speed, or the second to last thing, the average speed from 0 to 20 seconds. We need to find out how far this thing traveled at each interval. So from 30 down to 10, it traveled 20 meters. From 10 over to 25, it traveled 15 meters. So we're going to add those two numbers together, and our total distance is 35 meters. So remember, speed does not have a direction. So even though we're going down and then up, both of those are going to just be absolute value or positive numbers. So the total there is 35. Total distance is 35 divided by our time of 25 gives us 1.4 meters per second. If they want the average velocity from 0 to 20, we need to find the line that goes from here to the end. So from where we start at 0 time over to where we are at 25. You could also use the 20, but you really can't tell what the position is there. So because this is a straight line and we just need the slope to find the average velocity, we're going to use our 25 both for position and for time. So the slope of the dotted line is going to be 25 minus 30. Change in time is 25 minus 0. You get -5 over 25, so we get an average velocity of -0.2 meters per second. To find the velocity at 5 seconds, we need to do the slope of the line from 0 to 5 seconds. So from 0 to 5 seconds, we actually have the slope of this line to find the velocity at that point. And that would be 20 minus 30 divided by 5 minus 0, and that gives us -2 meters per second. Let's go ahead and go to the next page. A race car reaches a speed of 95 meters per second after it travels 450 meters past the starting line. If the car travels at a constant speed of 95 for the next 12 and a half, how far will it be from the starting line? So here, we're going to first take our 95, which is our speed, and we're going to multiply it times 12.5 seconds because it travels that 95 for 12 and a half seconds. That's 1,187.5 meters, but they want to know how far will the car be from the starting line because it's actually starting at 450 meters. So we're going to add how far we've traveled, and then we started at the 450, and so we end up with 1,637.5 meters. For the next section, they want you to plot the velocity, not the acceleration, but the velocity versus time for both object 1 and object 2, and then draw a motion map for each one. So here we've got object 2 has a bigger slope, so it should be on top. Object 1 has a shallow slope, so it should be on the bottom, but still above our dotted origin line. Let's go ahead and move this down a little bit so we can see our motion maps. So our motion maps for object 1, notice it has a smaller velocity. So these arrows are all the same, but they are shorter in length than the ones for object 2. Let's take a look at number 8. They wanted us to do the same thing, plus the velocity versus time for object 1 and 2, and then draw a motion map for each object. Number 1 has a velocity. Number 2 does not have a velocity. For number 1, we're going to just put 4 arrows here with the 4 dots starting at 0. And for object number 2, notice you don't want your dots here because it's not at 0. Instead, it is at some position to the right of 0, and those 4 dots, we're just going to just stack those to show that it's not moving. For number 9, they show a quantitative motion map for a dog fetching a ball. The dots indicate the position at each second, so I went in and put the seconds in 0, 1, 2, 3, 4, 5, 6, 7, 8. That way I know that I need dots at each one of the 8 times. My first dot is at 10 meters, and then I just went through and followed through with my dots and made my graph. Probably should have also gone through and labeled the graph so that it has everything on it that I need. I didn't do that on this one, obviously, but I should have. So let's go in and put these things in. So this is going to be position, so we'll just call that X and meters, and then this one is time, and it is in seconds. And so here we've got position versus time, and I'd actually spell out the word position and the word time, but just to keep this short, I didn't do that. All right, so let's move on. They want us to answer the questions based on the graph. So during what time interval was the object traveling most quickly in terms of speed? So here I went through and actually found what the speeds are for each one. I just took the path length divided by the time, and I found out that 1.33 meters per second was the highest speed, and that would be from 0 to 3 seconds. Next thing they want us to do is find the average speed from 0 to 12 seconds. So again, I have to find the change in position for this first slope, which would be 7 minus 3. And then I'm going to add 0. And then here I've got another 7 minus 5. And then I've got 0. And then I've got 5 minus 0. And that's all divided by my 12 seconds. So actually, this is not 7 minus 5. This one should be 5 minus 3. So this one is actually 5 minus 3 now that I take a look at it. So here we go. This is actually 5 minus 3 here. So that's 2. Either way, it's 2. We're going to take 4 plus 2 plus 5 divided by 12. 11 over 12 is 0.92 meters per second. So we're set with that one. They want us to find the average velocity from 0 to 12 seconds. You'll notice that I have traveled from here to here, so my change in position is 7. My change in time is 12, and so I'm going to have -7 because my final position is 0, original is 7, and I'm going to divide that by 12, and I get -0.58 meters per second. For number 11, so we'll back this guy back down, we have two position versus time graphs. These are accelerating, and so they want us to go through and draw the velocity and acceleration vectors for the motion map. On this one, notice that it's got a constant velocity, and then the velocity decreases. So we have a sad face here. I would always draw my faces before I do anything else. So here I've got a sad face. Over here, I've got my happy face, and that's a good thing. So there's my happy face. So I know that this one is speeding up, but notice it is speeding up in the negative direction. Okay, so it's traveling in the negative, so we see it's going to the negative, but it is accelerating, and it's accelerating in the positive, so it's got to be slowing down in the negative. Okay, so that's just a little bit confusing at times. We'll see here, this one's just got a constant speed, and then it slows down. This one has a decreasing speed, and then it has a negative constant speed. On the bottom, notice that the velocity is going in the opposite direction of the acceleration, and so it has to slow down. Here we've got just dots because it's not accelerating from here to here, but here it has a negative acceleration. Over here, this one has a acceleration that is, we're starting on this side, the acceleration's going in the opposite direction. So really we need to say where we're starting. So it's good to say here is where we are starting. So start, S-T-A-R-T, and going in this direction. So you'll see where this curve, it's smiling because our acceleration is positive, but it is slowing down because it is moving in the negative direction. Just another thing that confuses people just a little bit that we want to clear up. Next thing they want us to do, here I'll get out of my pen tool, is draw a velocity versus time graph. So here's our velocity versus time. It's got a positive velocity and then it decreases. This one has a big negative velocity and then gets closer to 0 and then it just stays steady. Our accelerations should match up with what we have up top, and they do. Here we've got a negative acceleration on this side and no acceleration there. Here we've got a positive acceleration. Remember, this one is moving. We've got to look at it going in this direction. Okay, oops. So let's blow this back up. So we're actually moving in that left to right direction. I mean right to left direction. So we'll move this back down. Here, remember, we're going in this direction, so these accelerations go first. Those are positive, and then we have no acceleration in the end. We'll go ahead and move this on up again and go ahead and take a look at number 12. From the graph to the left, they want us to write a physics equation. So here we've got velocity is equal to the slope, which is 2.86, but you have to figure out that it is a meter per second per second. So we either write meter per second or meter per second squared, and we multiply that times time plus 3.2 meters per second, and that's because that is our y-intercept and where we start. For number 13, we have a cart. It is rolling down an incline. They want us to notice the plus sign is to the right of the cart. And so if we are moving left, we are moving in the negative direction. Here's our motion map. We know that it should be starting at 0 and then it increases speed to the left. And so our acceleration should be the same all the way down. They want us to draw the correct position, velocity, and acceleration time graphs below for the motion of the cart. So we started at the very top and then we accelerate down. Okay, we accelerated down. We have a negative acceleration. That's why this is not smiling, it is frowning. So there is, whoops, one, and here we go. There's my other eyeball. So my eyeball is in my nose, and you'll notice it is frowning because it is accelerating in the negative direction. We started our velocity at 0, and it got bigger as we went down the hill. And then finally down here, we have a negative constant acceleration. For number 14, using this graph, they want us to find the velocity of the object at 2 seconds. And they want us to explain how we did it. So at 2 seconds, I can do one of two things. I can either find the slope of a secant line that goes from this point right here all the way over to this point right here. So I can just connect the two. Or I can do it from the 0 point, so we'll try to make a dot there. Let's use the pen, maybe it'll work better. So we're gonna do, we're gonna do a dot here and then go up to the point on the other side. So I'm gonna get rid of everything that I've drawn here, just a second. So I'm gonna grab this and we'll just get rid of those things. And I'm going to hit the delete key. There we go. And you'll see the line that I did was from, I've got my, this is my dot that I want right here. Okay, so there's my dot. That's the one I want to look at. So I'm going to go 2 to the left and 2 to the right and draw my secant line. The slope of that secant line is 8 meters per second, and that's how fast it's traveling at the 2 meters per, at the 2 second spot. At that 2 second spot. Next thing, they want us to use the graph to answer the following questions. Describe the motion of the object. So this one starts at negative 15 meters per second, has a positive acceleration, and it stops at 8 seconds. They want us to find the acceleration of the object and show our work. So we really just have to show the change in velocity over the change in time. So it finishes at 0 minus negative 15, which is positive, divided by 8 seconds altogether. And that gives us 1.88 meters per second squared. They want us to shade the portion of the graph that represents the displacement. So I've done that. And then we have to find out what is the velocity of the object at 2 seconds, but you can't just take it off of the graph. So to do that, we can find the velocity at 2 seconds and at 6 seconds, and then we can find the change in those velocities. So here, to find the velocity at each one, we know that the slope of the graph, so let's move this, this guy's gonna give me fits. We know the slope of the graph is 1.88. So we're going to use that, our original velocity, and the amount of time that we have to find out that the velocity is negative 11.24 meters per second, and here it's negative 3.72. Next thing they want us to do is find the displacement from 2 to 6 seconds. So you could either find the area here in that graph, or you could just use your equation, VF squared is equal to VO squared plus 2 times the acceleration times the change of position. And we know those two velocities, we know our acceleration, we know 2 is there, and we're just going to find that change of position. So either way would work. For number 15, a car initially at rest accelerates at a constant rate of 4, and it does that for 6 seconds. How fast is it traveling at 6? So just a plug and chug problem, pretty easy. Using the graphs, compare the following quantities for objects A and B. So the displacement for each one is the same because they have the same start and stop positions from here to here. The displacement from 0 to 1.5, though, is going to be bigger for A because it's higher up than B is, which is right here. For the next one, from 1.5 to 3 seconds, A is going to have a bigger displacement than B is because if for A, we're going to go from here to here. I'm sorry, A is going to be less than B because A, here, let's get rid of this. A goes from here to here and B goes from down here all the way up. So the change in position for B is bigger than it is for A, which is right there. The average velocity from 0 to 3 is the same because you go displacement divided by time. So we did that. The average velocity is going to be bigger for A than it is for B from 0 to 1.5, because remember our displacement was bigger. And the average velocity from 1.5 to 3 is going to be bigger for B because our displacement was bigger for B. And that's what you'll see there. Next thing we need to do is look at the instant velocity at 3 seconds. B has a bigger slope at 3 seconds. So when we go here, the slope for B is bigger than it is for A. So at 3 seconds, B has a much higher velocity. And the instantaneous velocity at 0 seconds is much bigger for A than it is for B. For B, it's about 0. So for A, it's bigger than the slope at 0 for B. Next page. For each of these position time graphs, they want us to draw the velocity versus time, the acceleration versus time. This one has a negative velocity, so we did that, and then it has no velocity because there's no slope there. The acceleration for this whole thing is 0 because there's no curve at all to your position versus time graph. Here, our position versus time graph, we'll go back, is we've got our eyeballs again, and so it's sad here. It's also sad here, so we know that your acceleration is negative the entire time. It starts with a really big positive velocity, because that's the slope here. It goes to a very 0 velocity, and then a very negative velocity over here. So we're going to go from very big positive to 0 to very big negative. The next graph, we have a smiley face again. So there's our smiley face. So we have positive acceleration, and then we don't have any acceleration here because our face is neutral. So that just goes here. Our velocity is very positive because our acceleration is positive. So we've got an upward slope, and then we don't have any velocity, or our velocity, sorry, is constant here. So we do have velocity, it's just very constant. For the next part, it says given the graph, sketch the shape of the other corresponding graphs. So same type of thing again. We have a very negative velocity to begin with. So the slope of the tangent line would be there. Here it's 0, and here it's very positive. So we can make a positive line there. So we're going to go from negative to 0 to positive. And our acceleration, this thing smiles the entire time. So it's smiling at the beginning, it's smiling here down at the bottom, and it's smiling over here on the right side. So we do have a positive velocity acceleration the entire time. Here we have a positive acceleration. Again, it's smiling. When it gets to about here, then it's constant all the way through, velocity and an acceleration that is 0. So here we've got a positive velocity. Here we have a constant velocity. On the last one, we notice, and I probably need to move this one a little bit. Here we've got a sad face, so we'll just put that there. Here we've got a sad face. We know that we've got just a neutral face at the beginning. So this one has 0 acceleration, and then it ends up having a negative acceleration. So it has a negative acceleration at the end. And so we have a positive velocity, and then we have a velocity that is decreasing, and hence the negative that you see there. Alrighty, let's move on to the next part. This is number 18. Consider the position versus time for objects A and B below. For velocity for A, we see that it's big, and then it gets smaller as we go. How do we know that? We could draw tangent lines at a few points here, and we see that those tangent lines go from very, very, very steep to not steep at all. Our acceleration, because it is a sad face, it's slowing down, needs to be going to the left for each one of those points. If we take a look at letter B, we notice that it is just a straight line, so it is a positive velocity. There is no acceleration at all there. So here's our positive velocities and our no acceleration. Describe how the motion of A is different from that of B. So A has a negative acceleration, B has 0 acceleration. They want to know about the displacement from 0 to 5 seconds. So from 0 to 5 seconds, the displacement is equal because you start and end up at the same points. The displacement from 0 to 2.5. So from 0 to 2.5, our displacement is bigger for A because we start at the same spot, but at 2.5, I'm a further position up than I am for letter B. And that's why you'll see that. The displacement from 2.5 to 5 is bigger for B because I am starting here at B and going up to here. And for A, I'm not traveling up as far. So B is going to be bigger than A for 2.5 seconds. The average velocity should also be equal. And then our displacement, remember, was bigger for A, so our average velocity will be bigger for A, but our displacement was bigger for B, so our instantaneous velocity at 5 seconds should be bigger for B. For 19, your teacher's car can go from 0 to 25 in 10 seconds. The car changes at a uniform rate, which means our acceleration is constant. They want us to draw a qualitative motion map. So here we've done that. We show that we went from 0, here's 2, 4, 6, 8, 10 seconds. And so we drew our motion map for that. And then we also have our acceleration down on the bottom. So it says qualitative, so you really didn't even need numbers there. Quantitative, velocity versus time graph, really you just had to do 0 to 10 seconds and 0 to 25 meters per second, and that's just a straight line because it has a constant velocity, an increasing velocity or a constant acceleration. Determine the acceleration, we just need to find the slope of the graph, so we took 25 minus 0 divided by 10, and we got 2.5. And so that is the number that we want. How far does the car travel in the 10 seconds? So the best thing to do here probably is to find the area of this triangle right here. And so we found the area of the triangle, 1/2 base times height. Our base is 10 and our height is 25, so that's 125 meters. The other way you could do it is use the equation change in position is equal to the original velocity, which is 0 times time, plus 1/2 of the acceleration, which we know is 2.5 times 10 squared, and you get the same answer. So you could do it either way. For number 20, the drawing below shows an object moving that's been photographed, and so I went ahead and I put times on each one, 0, 1, 2, 3, 4, 5, 6, and 7. And then they wanted us to plot a position versus time graph for that, and we did that. The next thing they want us to do is find the instantaneous velocity at 5 seconds. So if I want to do that, I can either go to 4 and 6 seconds and find the slope of a line that connects the two. So if I draw a line, here, let's do this. Draw a line from here up to here. Well, that's actually just delete that little guy right there. So if I find the slope of a line that goes from here, whoops, still doesn't want to do it, does it? From here to here. Or I can find the slope of a line that is 2 on either side of our point. So here's our point in question. It's probably easier to find the one that's 2 on either side. It's a little easier to see that. And so if I do all my math, find the secant line at 5 seconds. So I use 3 and 7 seconds. And to find it, to actually do it, I did 50 minus 9. Those are the 2 points on the secant line. 7 minus 3, so 41 over 4 is 10.25 meters per second. So here is my 50 and my 10, and then here is my 7 seconds and my 3 seconds. So I went through and did that, and I ended up with 10.25. If I want the average acceleration, I want to just take my change in velocity over change in time, so I did 10.25 over 5 seconds, and I ended up with 2.05 meters per second squared. For the next page, you just have some problems that you had to do. We have a bullet train. It's going from a speed of 50 to a speed of 40. So here we know that it is decelerating. We should have a negative acceleration. Does that in 500 meters. And so we used our equation, VF squared is equal to VI squared plus 2A times the change of position. Filled everything in, got negative 0.9 meters per second squared. So it's important that you see that that's negative. Rock is dropped from a bridge. It hits the water at 3.2 seconds later. They only give you one number, but don't forget that acceleration is equal to gravity, the acceleration of gravity, which is 10. Here we're saying that down is positive, and so we're going to take 0.5 times 10 times 3.2, so it is 51.2 meters high. Our original velocity, if you drop it from a bridge, so when you are holding it at the top, the instant you let it go, it's traveling at 0 meters per second, and then down at the bottom, it's traveling at a higher speed that we don't care about. The last question here for the football player, it's accelerating at 2 meters per second squared. If you start some rest, how long does it take him to travel 16 meters? We used our equation and plugged in and just got 4 seconds. Let's take a look at the very last one. We have our breakneck skier again. They want us to draw all of the forces without components, so we did that on the left. Don't forget your normal force needs to be perpendicular or have a 90-degree angle next to your slope. So we did that, and then we drew all of our components. Remember, you've got one component here and one here. Whatever your angle is right here, so this angle is 25. This angle next to the dot is also 25, as long as you draw one line that is perpendicular to the surface and one line parallel to the surface, and I try not to touch the lines at all, and then that way these two angles are the same. If you try to do this angle here, you've got to take 90 minus 25, and that would give you 65 for that angle. mg cosine on this side because it's adjacent, mg sine on this side because it's the opposite. So when we move this up, for the normal force, to find it, we're going to say that up is positive, down is negative. We know that the sum of the forces is 0, so we're going to take Fn minus whatever's going down, and notice that's mg cosine of the angle. There's nothing else going down. So the normal force is just mg cosine of the angle, plugged in the numbers, got the right number. To find friction, we've got to go everything in this direction minus everything in this direction, depending on which way we say is positive. But because we said x is positive in this direction, we're going to take mg sine of the angle minus the force of kinetic friction. So that's why we did that. And we get our final answer of 338 newtons. I hope you've enjoyed learning with me. I have enjoyed learning, as Jonathan Palmer Thomas says, with you.